Assalamualaikum warahmatullahi wabarakatuh. For today's presentation, we are going to talk about one of the chemical reactors. And the reactor that we have chosen is Cstr, Continuous State Tank Reactor. And this presentation will be presented by me, Nazatul, Fauziatul, and also Batrisha. Alright, so what am I going to talk about? I'm going to introduce to you what is Cstr. Continuous Steam Tank Reactor (CSTR) is one of the continuous flow reactor which is used for facilitating the chemical manufacturing with continuous flow. CSTR work with minimal contamination, but it is able to optimize the conditions control. It also works at the constant temperature, constant pressure, and also the constant concentration of the reactants. And because of this, they have the less consumption of resident time distribution, which is RTD. And CSTR are also able to achieve the higher efficiency and the higher chemical yields. And CSTR also have the same composition of the input and output of the feedstock. So basically, CSTRs have no decrease or increase volume. So I'm going to talk about the working mechanism of CSTR. So firstly, feed introduction. What is that? So basically, the reactants or the feed will be introduced into the reactor tank continuously at a constant flow rate. And after that, the agitator of the reactor will spin continuously to mix the feed uniformly to produce a homogeneous mixture. And thirdly, we have reaction zone. The product will undergo the chemical reaction with the exposure of catalyst if required at a controlled temperature, pressure, and also the concentration of the reactants. And after that, the product will be removed from the reactor via outlet stream at the same rate as the feed enter the reactor tank. So basically, they will achieve a constant reactor volume. Afterwards, at the steady state operation, the system will be assumed to have reached the equilibrium where the concentrations of reactants and products are constant. And lastly, we have flow dynamics. CSTR ideally aims to achieve the perfect mixing with the constant temperature and concentration, constant reactor volume, and also the effective steady-state operations. Alright, next I'm going to talk to you and present to you the diagram of CSTR. So firstly, as you can see here, we have motor. So what is the function of motor? So the motor of the CSTR will be used to start and steering the agitator. Then we have the cooling jacket, which is used to control and maintain the rate and temperature of the chemical reaction. Then we have inlet stream. This is where it allows the entrance of feed or reactants into the reactor tank. Then we have the baffle at the side of the tank vessel, which is used to increase the efficiency to mix more complex products. Then we also have the agitator, like is the spinning fan, which is used to continuously mixing the reactants uniformly to produce it into the homogeneous mixture. And lastly, we have outlet stream. A well-mixed product will leave the reactor via the outlet stream. So, I think you might be wondering, does CSTR look the same? The answer is no. Why? Because CSTR has some configuration such as single CSTR, CSTRs in parallel configuration, and also two CSTR in series configuration. Alright, since CSTR is one of the catalytic reactor, what are the types of catalysts that are used for CSTR? We have homogeneous catalysts, heterogeneous catalysts, and also biological catalysts. Homogeneous catalysts are the catalysts that are in the same phases as reactants and is soluble in the solution, which is commonly liquid. So the examples are acid and base catalysts like sulfuric acid, which is used for the esterification, and also sodium hydroxide, which is used for saponification. We also have organometallic catalysts such as Wilkinson's catalyst for the hydrogenation, and also the Grubbs catalyst, a ruthenium-based complex catalyst for olefin metathesis. Next, we have heterogeneous catalyst. So heterogeneous catalyst is present in different phases with reactants to provide the chemical surface where the chemical reaction takes place. But this catalyst is easier for the separation between reactants and also catalysts. So some of the examples are metal catalysts such as platinum or palladium for the hydrogenation, and also nickel for margarine production. We also have example for metal oxide catalysts such as vanadium pentoxide for oxidation of CO2 into CO3. Then we have zeolites, which is a zeolite-based catalyst that are used for fluid catalytic cracking, FCC. Next, lastly, we have biological catalyst. Biological catalyst is like the enzyme or proteins which is used for bioreactor environment in order to facilitate the microbial or biochemical reactions. This is due to the presence of the active site in the catalyst. So, some of the examples that we have are enzymes catalysts for biofuel production such as cellulose and silanase. The enzymes that are used for pharmaceutical industries, we have penicillin, acylase, and also lipase. The enzyme for waste treatment, we have protease, cellulose, and also lactase.
The next part, the application of Cstr. The first one is chemical manufacturing. It is ideal for liquid phase reaction where temperature and concentration are important to determine reaction rate. It also perfect for reaction that require constant mixing and steady conditions such as sulfuric acid production because it's effective heat transfer. The second one is wastewater treatment. Cstr are commonly used in activated sludge process which help to keep oxygen-dependent microorganisms active and breaking down the pollutant. The constant mixing of Cstr ensures microbes distribute evenly in contact with contaminant. It also easy to control for treatment efficiency. The third one is petrochemical industry where it is used in catalytic cracking and hydrogenation such as diesel production from crude oil. Continuous stirred reactor provide uniform mixing and temperature control to boost efficiency. It also helps to maintain steady operation for effective conversion in exothermic reaction. Next is pharmaceutical industry, which help in continuous manufacture of active pharmaceutical API. It enables precise fermentation control for microbial processes. The better product consistency causing high yield, reduced maintenance, and lowering the contaminant risk. Other than that, it is also used in food and drink processing, commonly in homogenization, pasteurization, and fermentation, because it ensures constant flow and suspension of microbes for products like yogurt and wine. The continuous mixing distributes nutrients evenly and precise pasteurization without affecting the flavor or nutrition of the product. Next is advantages of continuous stirred reactor. Firstly, is the uniform quality of the product. It is used in pharmaceutical, specialty chemical, and fruit processing because continuous mixing eliminates concentration gradient while maintaining a steady temperature, pressure, and concentration that can minimize the effect of the product. Secondly, the scalability. This is because of the easy transition from lab scale to large scale system without changing the reaction process. The continuous flow, stirring, and mixing are consistent across reactor sizes. Hence, adjusting the reactor size, flow rate, and heat transfer make the scaling smoother and can reduce errors in production. Next is cost efficiency, where Cstr has lower maintenance costs compared to batch reactor. It also maximizes the production time, reduce material and labor waste because of the continuous operation. The precise temperature control reduces energy consumption, making this reactor cost effective for long term and high volume production. The last one is versatility across reaction. Cstr is ideal for both homogeneous and heterogeneous processes where it is used in fermentation, petrochemical, polymerization, and wastewater treatment. This is because it can control the residence time, temperature, and pressure for different processes and minimize issues like catalyst deactivation and ensures consistent product quality. Next, I'm going to talk about the weakness and solution of Cstr. The first weakness is poor mixing in large scale. It can be solved by adjusting the size, shape, and speed of impeller to improve the flow. We also can install buffers to prevent swirl formation and use multi-stage reactor to specific process. The second weakness is poor heat transfer. It needs jacket and internal coil for heating or cooling to maintain temperature control. Heat exchanger also can be used to absorb or generate heat as needed and improve heat management in larger reactor. The third one is risk of side reaction. We need to monitor reactant composition, temperature and pressure to improve purity and selectivity. By using intermediate purification method like centrifugation or membranes, it can prevent degradation and side reaction happen. Next is dilution issues. It can be solved by adjusting feed concentration in the reactor or recycle effluent to maintain higher reactant concentration. Series of CSTR also can be used to improve reactant concentration and efficiency. The last one is uneven residence time, where it needs to maintain steady state operation to optimize residence time. The multiple CSTR series can reduce short-circuiting. Other than that, the use of computing fluid dynamic models also can optimize residence time distribution.
Assalamualaikum, my name is Patricia and I will talk about the industries of CSTR. CSTRs are vital across multiple industries such as pharmaceuticals, petrochemicals, food and beverages, textiles and agrochemicals. In pharmaceuticals, CSTRs are essential for synthesizing active pharmaceutical ingredients or APIs and intermediates. Their continuous manufacturing process reduces batch-to-batch variability, ensuring high-quality medicines. They are also used in fermentation and cell culture to create optimal growth conditions. In the petrochemical industry, CSTRs are employed in polymerization and refining operations. They maintain uniform agitation and precise temperature control, which is crucial for product quality. Additionally, they help mix additives into fuels and lubricants, enhancing their performance. CSTRs are widely used in the food and beverage industry, ensuring consistent formulation and quality in fermentation, emulsification, and mixing processes. Whether it's yogurt, beer, or salad dressing, these reactors help maintain uniformity in flavor, texture, and nutritional content. In textiles, CSTR play a crucial role in dyeing and finishing. Their continuous mixing action ensures consistent color and quality. They also facilitate the application of finishing agents that enhance fabric properties such as water resistance and flame retardancy. Finally, the agrochemical industry benefits from CSTRs in the synthesis of herbicides, fungicides, and fertilizers. These reactors enable efficient production of nitrogenous and phosphatic fertilizers as well as fermentation for biofertilizer production, supporting sustainable agriculture. Next is derived design equation and suggest raw data. First, I will talk about derived design equation for CSTR. First of all, we have mole balance, which is V equals to FA0 minus FA over negative RA. That will be our equation 1. Next is the conversion, which is X is equal to FA0 minus FA over FA0. That will be our equation 2. In order to make FA as our subject, we must multiply FA0 with X. With that, our last and the third equation would be FA equals to FA0 minus FA0X. Then we will combine equation 1 and equation 3. As you can see, we can cancel out FA0 with other FA0. This will produce our last and final equation, which is V equals to FA0X over negative RA. Second is suggesting raw data. Here I suggest the data with the table provided. We have conversion X, the reaction rate negative RA, the reciprocal of the reaction rate 1 over negative RA, the molar flow rate FA0, and the calculated values of FA0 over negative RA. By using this data, we can determine the reactor volume at different conversions. Beside the table, we have the Levin spill plot. On the x-axis, we have the conversion, and the y-axis, we have the FA0 over negative RA. The area under this curve gives us the required reactor volume. The volume can be determined by using this formula, which is FA0X over negative RA. Alternatively, we can also calculate it as the area of a rectangle in the Levin spill plot, which is volume equals to height times width. For example, volume equals to 0.8 times 8.000, which we will get 6.4 meter cubic, which turns out to be 6,400 dm cubic. By applying this formula to all the values of X, we can determine the volume at each conversion point. This helps in reactor design, ensuring the correct volume is selected for optimal reaction performance.